Hello all, welcome back to yet another video of the today's lead code daily challenge. The problem is remove stones to minimize the total. You are given a zero indexed integer array piles where piles of I represents the number of stones in the ith pile and an integer k. You should apply the following operation exactly k times. So choose any piles of I and remove floor piles of I by 2 stones from it. Notice that you can apply the operation on the same pile more than once. Return the minimum possible total number of stones remaining after applying the k operations. So floor of x is the greatest integer that is smaller than or equal to x. That address rounds x down. So that is nothing but the rounding of x. If 5 by 2, then we want to take it as 2, not 3. So okay, let us see the examples. So the piles are 5, 5, 4 and 9, and where our k is equals to 2. So we can take k piles. We can do k operations to be set correctly. So actually, sorry, floor the greatest integer. Sorry, the floor of x is the greatest integer that is smaller than or equal to x. So we have to round off the 9 by 2, then we want to take it as 5, not 4. I have said previously wrong, but hope you understand now. If it is 5 by 2, we have to take it as 3, not 2. So okay, now let us analyze this example 1. The piles is 549 and k is 2, so we have to do two operations. So we want to get the minimum possible total number of stones remaining after the applying the k operations. So steps of possible scenario are applying the operation on pile 2. So if we apply an operation on pile 2, then this looks like 5, 4 and 9 by 2, which is 5. Next, the when we apply the operation on pile 0, if we apply the operation on pile 0, let us name those index 0, 1 and 2. If we apply the operation on pile 0, then it looks like 5 by 2, which is 3. It is 2.5. If we round off, it is 3 and 4 and 5. We have done k operations, and after applying two operations, the resulting piles are 3, 4 and 5, and the total number of stones is 3, 4, 5, which is 12. So the sum of this is nothing but 12. So this is we have to return that sum of stones that are left after k operations. So we want to minimize this possible sum. Let us take this 5, 4, 9 once again, and let us apply in different scenario. If I take the pile 0 and apply one operation, then it becomes like 5 by 2, which is 2.53. So 3, 4 and 9. This is nothing but pile 0. I have taken pile 0 and divided by 2. Now again we can take. So here we have affected the pile 0, and the second scenario, let us uh, take the first pile, that is the pile 1, and we can divide it by 2. So if we perform that operation, if we remove the second pile, which is 3, 2, 9, then the total sum looks like, the total sum is nothing but 3 plus 2 plus 9, which is nothing but 14. So we are having a sum of 14 when in this scenario. We have a sum of 14 in this scenario. So in this scenario we got a 12, and this scenario we got a 14. As you can observe that we want to minimize the total sum after removing the total number of stones using those k operations. So to minimize the sum, we want to actually remove the larger pile having the larger stones. That is, if we remove the pile which is having a larger number of stones, then we will be minimizing the total sum. If we remove the smaller pile in the sense, if we remove a pile which is having small few number of stones, then this is going to maximize our total sum. So hope you understand what is happening here. If we remove a pile which is having more number of stones, then we can reduce the sum. If we remove a pile which is having few number of stones, then we will be maximizing the sum. So our question states that we want to minimize the total sum after removing the stones using those k operations. So by that way we can get this we will tend to remove the larger number of stones which is in the pile. So this is one intuition. If there is 5 4 9, first we can tend to remove this 9. Then if we remove 9, then we are doing one operation, so it becomes 9 by 2, which is 5. And in our second operation, either we can remove this pile or this pile, so both are having same value 5. So if we remove even this 0 1 2 pile 2, then it becomes 2 by 2, which is 3. Sorry, 5 by 2, which is 3, and the total sum is nothing but 12. So after k operations we can get a minimum sum of after k operations is 12 in this scenario, in this problem, in this example. So hope you understand the logic behind this. So one such thing what we can do is we can sort the array each and every time after removing the larger number of stone, but that is going to be n square log n time, and it is not much efficient. That is nothing but a brute force solution. Each time we will be finding the maximum and we will be dividing it by 2. This is going to be an n square solution. So how can we reduce that quadratic solution to a smaller more efficient time complexity? So we can for each time we tend to take a maximum or the minimum pi. So each time we tend to take a maximum or minimum pile, but in this problem, according to this problem, we want to take the maximum pile having the maximum stones. So each time we want to take the maximum stone, so how can we instead of going and traversing each time and finding the maximum element, we are having a data structure called heap that can give you a minimum or maximum element in order of log n time. So since we can we can reduce the time complexity to much better than n square using this heap data structure. So if we for this problem we can use a max heap where we can find where we can push all the elements into our priority queue. The max heap is nothing but the priority queue. It is going to give the maximum element in log n time. So so we can push all the elements into our priority queue. So each time we can pop out one element which is going to be the maximum element, that is the maximum pile, and we can divide by 2, and if it is going to be greater than 0 we can just push that back into our priority queue. So by that way what we will be doing is we are going to process n elements, and there will be k operations, right? So sorry, so the priority queue, the time complexity is going to be log n for one for taking out one maximum element. So if there is going to be n elements, there is going to be log n, and there will be k operations, so k into log n. So we can say it as the time complexity will be k log n. So this log n is nothing but the inbuilt sorting that is done in priority queue. So that is the log n, and this k is going to be, we are doing a k operations. K operations in the sense we will be taking out the k elements. So this is the time complexity for this problem, and the space complexity will be order of n, since we will be pushing all the elements into our priority queue. So now let us try to code the approach. So we need a maximum heap, so which is nothing but the priority queue into pq. I will name it as max heap. Now what we can do is, so we want to insert all the elements into our max heap. So for auto pile in my piles, max heap dot push of this pile. So now we have inserted all the piles into our max heap. Now what we can do is, we want to perform the k operations. So we can have the total sum is to be 0 initially, and we can return this sum at the end of the day. So while my priority queue is not empty, pq dot empty, while my priority queue is not empty, we can, what we can do is, we can add it to our sum plus equal to pq dot top and pq dot pop. Sorry, pq not, it is max heap. My bad. If my max heap is not empty, I will add it to my sum, and max, I will pop out the element. So this is done at the end of the day. But before that, what we want to do is, we want to perform the k operations. So we can have a while k minus minus. If while k minus minus and if my priority queue max heap is not empty, if it is already empty, we don't want to do anything. What we can do is, first we can take the top element is nothing but the max heap dot top, or we can say it as pile, int pile. And what we have to do is, pile is nothing but pile divided by 2 plus pile mod 2. So this is a simple technique where we can take the seal value. Seal value in the sense, we can round it off to the greatest value. So pile divided by 2 plus pile mod 2 will give, this will nothing, this is nothing but this operation. We have done this operation which is required for this problem. We also want to pop it out, so we can just pop that element. So now what we can do is, if my pile is going to be greater than 0, then we can just push it into our max heap. So that's it. It is as simple as that. So now let us try to run our code. Great, it gets accepted. Let us submit our code. Superb, it gets accepted. Hope you like the solution, and let me know in the comments if there are any suggestions. Let us see in tomorrow's LeetCode daily challenge. Until then, bye.